Related rates. Now that we have studied implicit differentiation, let's see how we can apply implicit differentiation to problems involving related rates. Related rates is an application of implicit differentiation in real-life situations. In simplest terms, related rate problems are problems in which you need to figure out how fast one variable is changing when given the rate of change of another variable at a specific point in time. For example, how fast is the radius of a balloon growing when being filled at a particular rate? Or we might consider how fast is the water level rising when a tank is being filled at a particular rate. Let's analyze a specific problem just to get the feel of how to solve these types of problems. We know these problems can be overwhelming, but are simple when broken down. Let's look at an example without actually solving it, just to get an understanding of the process and the steps we will need to take to solve these types of problems. And the example we're going to look at is that a spherical balloon is being filled with air at a rate of 20 cubic feet per minute. How fast is the radius changing when the radius is 2 feet? So let's note that this 20 cubic feet per minute is the rate at which the air is changing or going into the balloon. That was going to denote the change in volume. What we're looking for is how the radius is changing, so eventually that'll be our dr dt, and it's going to occur at the instant the radius is 2 feet. Let's continue on. It's often helpful to draw a picture just to get a visual of what's going on. So if we draw the picture, we're going to treat the balloon as a sphere, three-dimensional ball. The radius will be the distance from the center point of the balloon all the way around, and we have the air going in. Next, we're going to label the picture with what information we can. So the air going into the balloon is changing the volume. So that's going to be denoted as dV dt. dV dt is the rate at which the air is going into the balloon, as it represents the change in volume with respect to time. Next step, we're going to identify just the rates of change. So we're told up here that the rate of the volume is changing at a rate of 20 cubic feet per minute. So that is going to be our dV dt. What we need to do is find dr dt at the moment the radius is at 2 feet, because that represents the change in radius with respect to time. Now, we need to come up with an equation that relates dV dt and dr dt. So the balloon is a sphere, and while we don't have an equation for the rates, we do know that there is an equation that relates volume to the radius, and that is the volume formula for a sphere, given right here. So it might be a good idea for you to pause the video, see if you can differentiate v is equal to 4/3 pi r cubed implicitly, and then after you finish, restart the video and compare your answer with what I'm about to show you. If you did it correctly, you would have dV dt is equal to 4 pi r squared dr dt. Now, notice that how the equation of the derivative has two known values and one unknown. We know that dV dt is equal to 20 cubic feet per minute. We know that r is 2. What we need to find is dr dt. That's what we need to solve for. So at this point, it's clear that we would substitute the known values and solve for dr dt. But before we do, let's recap the different steps that we took. You may want to pause the video here or refer to your notes, and if you're a person who needs extra reinforcement, it may be wise for you to write down these steps in your own hand so that they're easy for you to remember, or at least have them handy as you're approaching the next couple problems. I'll read them out loud to you. Number 1, draw a picture and label any known variables and constants. Number 2, identify the given and needed rates of change. Number 3, find a formula or equation that relates to variables whose rates of change are given with those needed at times, and this could be provided. Number 4, implicitly differentiate with respect to time. Typically, it's going to be t. Number 5, substitute in the values you know and solve for the rate of change you need to find. Number 6, be sure to answer this question, even if it means writing the answer in sentence form. A little word of warning. It's very common for us to make this mistake. The most common mistakes in these problems are made because we tend to substitute too early. Do not substitute until after you differentiate. So perform your differentiation first to get your rates of change, and then put all your substitutions in. You'll find out that typically that works. Remember, you can only substitute known values into the derivative of the equation. Now we're going to go ahead and finish up that example and find out what the actual answer is for DRD2.